Welcome to this explainer. Today we're diving straight into the architectural blueprints of modern chemistry. We are looking at the monumental legacy of the Dutch chemist Jacobus Henricus van Hoff. Now you might actually recognize that name because he took home the very first Nobel Prize in chemistry way back in 1901. But what he actually achieved to earn that is nothing short of mind-bending. He essentially provided the mathematical key that connected microscopic, completely invisible molecules to the massive macroscopic world of thermodynamics. And today we're going to see exactly how he pulled it off.
So, here's a wild thought to get us started. How does a single mathematical rule feed 8 billion people on Earth, predict the trajectory of global climate change, and even unlock the microscopic secrets of how proteins fold inside our own bodies? I know, it sounds like absolute magic, but I promise you, as we zoom in from giant global phenomena down to elegant, single mathematical rules, it is all going to make perfect, logical sense.
Okay, let's dive into this. Here is our roadmap for today's explainer. 1. Master architect of chemistry. 2. The dance of temperature and equilibrium. 3. The speed of life. 4. Colligative properties. 5. Gas dynamics of osmosis. And finally 6. The great approximations.
Number 1. Master architect of chemistry.
To really get why Van Hoff is such a huge deal, we kind of have to look at what chemistry was like before him. Before his monumental 1884 book, Études de dynamique chimique, chemistry was, well, largely phenomenological. Scientists would mix things together in a lab and just watch to see what happened. But Van Hoff completely shifted that paradigm. He defined exactly how chemical reactions reach equilibrium as a strict mathematical function of temperature and energy. Literally overnight, he elevated chemistry from pure observation into a predictive, quantitative science.
Moving right along to part 2, the dance of temperature and equilibrium.
The Van Hoff equation dictates what I like to call the dance of temperature and equilibrium. Think of a chemical reaction at equilibrium like a perfectly balanced giant tug-of-war. But what happens when you introduce the stress of temperature changes? Well, according to Le Chatelier's principle, the system is going to fight back to restore balance. In an endothermic reaction, the system naturally absorbs heat. So if you raise the temperature, the system tries to relieve that stress by soaking up the extra heat, shifting the equilibrium forward to pump out more products. Exothermic reactions, on the other hand, naturally release heat. So if you heat that system up, it fights back by slamming the brakes on the forward reaction, shifting backward just to restore stability. It's this constant, dynamic dance to minimize stress.
And this brilliantly illustrates one of the most absolutely crucial industrial applications in human history, the Haber-Bosch process for synthesizing ammonia. Just take a second to look at these massive numbers. 200 atmospheres of pressure, 400 to 500 degrees Celsius. These extreme, brutal conditions are entirely dictated by Van Hoff's principles.
Because here's the catch, the dramatic Haber-Bosch dilemma. We desperately need ammonia for synthetic fertilizers to literally feed the world, but thermodynamically, creating it is an exothermic reaction. That means it actually prefers freezing cold temperatures to maximize the yield. But here is the kinetic reality. Nitrogen molecules have a massive, super strong triple bond. If you run the reaction at freezing temperatures, you're going to be waiting centuries to get your fertilizer. So engineers have to blast it with intense heat, 400 to 500 degrees, and throw in an iron catalyst just to break those bonds quickly. But wait, we just said that high heat pushes the equilibrium backward. So to fix that new problem, they crush the gases under 200 atmospheres of pressure, forcing the molecules together to decrease entropy. It is a breathtaking balancing act of physical chemistry.
All right, section 3, the speed of life and the Q10 index. Let's step out of those massive industrial chemical plants and zoom right into the biological world. Van Hoff's insights evolved to explain the very reaction kinetics that dictate life itself. To help us understand biological speeds, he gave us the Q10 temperature coefficient. This is a brilliant, totally unitless multiplier. It tells us exactly how much a reaction rate exponentially increases when the temperature of a system rises by exactly 10 degrees Celsius. It's the ultimate measure of how temperature directly amplifies biological speeds.
When we actually break down these values, the real-world implications are massive. For simple physical ion diffusion, the Q10 is about 1, which means a 10-degree bump really doesn't change much at all. But think about enzyme activity, or mammal respiration, or plant photosynthesis. Their Q10 sits between 2 and 3. That means a mere 10 degrees Celsius bump literally doubles or even triples ecological metabolic rates. This is exactly why the Q10 coefficient is an absolutely crucial mathematical parameter in modern climate change models today. And if you look at large protein deformations, the value skyrockets above 3, which points to some extreme temperature sensitivity.
Next up, section 4,
colligative properties in the factor I. So shifting gears to non-ideal aqueous solutions. Back in the day, scientists were making some massive calculation errors regarding colligative properties. We're talking about things like boiling points and freezing points. Van Hoff swoops in and fixes this with what we now call the Van Hoff factor, represented by the letter I. Basically, it's a scaling multiplier. It's the ratio of the apparent number of dissociated particles floating around in a solution compared to the original number of moles you dumped in. If you dissolve sugar, it stays as one whole unit, so the factor is 1. But if you dissolve table salt, NaCl, it splits into 2 separate ions, so the ideal factor is 2. It's a remarkably simple multiplier, but it perfectly fixes the math for freezing point depression and boiling point elevation.
Now, what's really interesting here is the gap between ideal theory and measured reality. Take sucrose. Ideal is 1, measured is 1. Perfectly behaved. NaCl splits into 2. Ideal is 2, measured is 1.9. Hey, pretty close. But check out magnesium sulfate, MgSO4. It splits into 2 ions, so the ideal factor should definitely be 2. But the measured reality is a drastic drop down to 1.3. It's acting almost like a single solid particle. Why on earth does it do that?
Well, the mystery was eventually solved by the Debye-Huckel theory of ion pairing. You see, magnesium and sulfate ions don't just have simple single charges, they pack a powerful +2 and -2 electrostatic punch. When they're swimming around in solution, they pull on each other so intensely that they form temporary clouds of electrical ion pairs. So instead of floating freely as 2 independent particles, they clump together and act as a single unit. This effectively hits the brakes on the Van Hoff factor, dropping it all the way down from 2 to 1.3.
Section 5. Gas dynamics of osmosis. This is where Van Hoff really shows off his unparalleled ability to link seemingly completely unrelated physical properties. He connected fluid osmosis straight to kinetic gas theories. Let's set the stage historically. In 1877, a botanist named Wilhelm Pfeiffer designed an artificial semi-permeable membrane. He discovered something wild. A highly dilute, mere 1% sugar solution generated a massive 2/3 of an atmosphere of mechanical hydrostatic pressure as water rushed in. This piece of dormant botanical data completely stumped the greatest physicists of the time for an entire decade. Literally nobody could figure out the math for it. That is, until Van Hoff looked at the data and made a totally radical, absolute genius of an analogy. He realized, hey, we can treat these solute particles in a highly dilute solution exactly like gas molecules zipping around in an empty room. So he just takes the ideal gas law, PV equals nRT, and seamlessly transforms it into the equation for osmotic pressure, pi equals CRT. By treating dissolved sugar as if it were a gas hitting the walls of the membrane, he solved a decade-long botanical mystery using pure physical chemistry. Boom!
And finally, Section 6, the great approximations and modern corrections.
So, the crucial point we really have to make here as we look at this from a modern perspective is that Van Hoff's 19th century linear models were revolutionary for sure, but they definitely weren't perfect. It's summed up perfectly by this thought. These equations are a rough yet wildly powerful approximation model that barely holds true only under conditions of extreme infinite dilution. You see, Van Hoff's models assumed that the heat capacity of a system remained perfectly constant regardless of temperature. Now, that was a brilliant assumption to get the math to actually work back in the 1800s, but it's flawed today because it ignores the massive, shifting heat capacities we see in complex systems, like when biological proteins unfold.
Today, we bypass those old linear limitations with modern computational chemistry. First, scientists use ultra-precise tools like calorimetry to observe those nonlinear heat capacity shifts. Then, they apply Kirchhoff's temperature compensation laws. And finally, they convert Van Hoff's straight linear graphs into beautifully complex, highly accurate multi-degree polynomial functions. We've basically taken his incredibly solid 19th century foundation and built a 21st century skyscraper of precision right on top of it.
Which brings us to our final lingering question for today. How did an imperfect approximation become the most perfect cornerstone of human civilization? Van Hoff's equations were technically flawed limits, absolutely, but they were so profoundly visionary that they built the literal foundations of our modern industrial and biological world. From the synthetic fertilizer that feeds billions of people to the complex climate models that are trying to protect our future, his legacy is literally everywhere. Thanks so much for joining me for this explainer. Keep questioning the world around you, and I hope this leaves you wanting to explore even more about the hidden rules that govern our universe.